Okay, welcome to 9.2. 9.2 is an excellent review of chapters 7 and 8. We're going to go through all of that again. Just a reminder that chapter 9 started with a discussion of being able to differentiate between matched and independent samples. So if you need to, go back and take a look at that again. We're going to be talking about matched, paired, or dependent samples. So that's our topic for 9.2. Now there are some shortcuts here. Now first off, if the lists are of different lengths, if you've got a different number of one thing and another, they are in no way matched. They have to be independent. Now if they are the same length, if you have as many of each sample, you then have to ask the question, can you match? Or is there an element that goes with each of the first list with each of the second? So two things have to happen. There has to be exactly the same length. If there isn't, you know they're independent right away. And if they are the same length, you have to be sure that they're matched in some way. We're going to see an example where we're talking about a single patient at two different times as they recover from a heart attack. Now, if you are talking about matched pairs, so that's where we are right now, we're talking about matched pairs. And if you are talking about matched pairs, then there is a shortcut, and that's basically taking you back to chapters 7 and 8. We form the differences, and then we do the single sample statistics, whether it's a hypothesis test or a confidence interval, for that list of differences. And those differences, D, are formed by taking x sub 1 and subtracting x sub 2. So a lot of things that were x's in the example that we saw in chapter 7 are now d's. So take a look at what that means for the sample mean of the differences. So that second example, notice, instead of x bar, we now have d bar. It's formed by the sum of the d's divided by n. So we're now looking, basically, that d is telling us that we're looking at that list of differences. And then, of course, we have the standard deviation of the differences, so s sub d. And the standard deviation of the differences is exactly what you'd expect, except the x's have become d's. Now, the test statistic is of the same ilk. The only difference here is that x's have become d's. One of the other things that I want to point out, and we'll see this in just a few seconds, is that in this formula we need to know what mu sub d is. That is the mean of the differences. But this is a hypothesis test, and hypothesis tests often tell us some information. We're allowed to assume the null hypothesis. And so notice that in most cases, the null hypothesis is that there's no difference between the two populations. That is, that the mean of the differences is 0. So that makes this formula just a tad nicer. So here is an example. So we're looking at the cholesterol level of patients who had heart attacks. We measured those 2 days after the heart attack and then again 4 days after the heart attack. The researchers wanted to see if the cholesterol level of patients who have heart attacks reduces as the time since their heart attack increases. In other words, does the amount of cholesterol go down from 2 days after a heart attack to 4 days after a heart attack? Do the data show that the mean cholesterol level of patients that have had a heart attack reduces as the time increases? So that's our alternative hypothesis. We're going to say we're testing to see if that is indeed the case. Now, and it says to test at the 1% level of significance. So here's our data. So you can pause the video. This is exactly the same as in our workbook. The data is paired. So notice that we see that patient number 1 has 2 pieces of data. We know that the cholesterol level after the second day for that patient was 270, and after the 4th day was 218. In other words, we can match up data from the first list with data from the second list. But that patient information tells us that the information that we're actually being given is in fact matched. So the first thing we do is we state the random variable in words. And to do that, we remind ourselves that there are two. So X sub 1 is the cholesterol level of a single patient 2 days after a heart attack. And then X sub 2 is the cholesterol level of a patient 4 days after a heart attack. So what that means is that we can find D. And D is the difference, that is X sub 1 minus X sub 2. The parameters are the population means. So mu sub 1 is the mean cholesterol level of all patients 2 days after a heart attack. And no great surprise, mu sub 2 is the mean cholesterol level of all patients 4 days after a heart attack. And this is perhaps more important. Mu sub D is the difference of those population means, mu sub 1 minus mu sub 2. Now that's important because in a hypothesis test we do get some information from the null hypothesis. Remember, we're allowed to assume the null hypothesis. So we're going to say that the null hypothesis is that there's nothing really going on, that the two population means are the same. Mu sub 1 equals mu sub 2. Now notice that this is you can call it an algebraic expression. We could subtract mu sub 2 from both sides. And if we do that, we get that the mu sub D, that is the mean of the differences, is equal to 0. If you subtract mu sub 2 from both sides, you get a 0 on the right side, and you get mu sub D on the left side. So we're allowed to assume that. Remember, we're assuming the null hypothesis. Now, the alternative hypothesis comes from what it is that we are trying to establish. And we are trying to establish that the amount of cholesterol in heart attack patients reduces. That is, that the population mean 4 days after a heart attack, that is mu sub 2, is less than the amount of cholesterol 2 days after a heart attack, that is mu sub 1. So stated in the same order, 1 to 2, that says that the cholesterol levels were higher 2 days after a heart attack than they were 4 days after a heart attack. So we've got that inequality. Again, we're going to have to subtract mu sub 2 from both sides and get that difference. So our alternative hypothesis, when we subtract mu sub 2 from both sides, remember we're still using that definition of mu sub D, which is mu sub 1 minus mu sub 2. And the moment that we have that, subtract mu sub 2 from both sides, we have the direction of our inequality. So when we enter the alternative hypothesis into the calculator, we're going to say that mu sub D is greater than 0. This is also where we state the level of significance. In this case, alpha is 0.01. Now we have to go through and check our assumptions. It does not say that either sample is random. So at this point, that's exactly what we have to do. Now, the second thing that we're interested in showing is that this is a normal distribution. So this is when we have to remember that some things like intelligence and height and cholesterol levels we're allowed to assume are normally distributed for the purpose of this class. So that means cholesterol levels are known to be normally distributed. We don't have to worry about the sample size or anything like that. And remember, the last part of this test is basically ensuring that we're doing the correct test. And that is, we're doing a t-test. Why are we doing a t-test? Because the population standard deviation is not known. So let's go into our apps. Let's select those two columns of the cholesterol data. Let's copy. Then go into GeoGebra. Let's turn on spreadsheets, turn off graphics and algebra, and let's paste in that data. Looks like we got all 30 data points. Now we're interested in the change in the cholesterol levels, so we're going to go into the next column, press equals, because we want it to do some arithmetic, and we're going to ask it if that cholesterol level has changed. Now notice the way that I set this up. A larger first cholesterol level minus a smaller second cholesterol level, like we have in this first case for this first patient means that we have a positive difference. Now, the way I set that up means that when we test this, we'll have to be testing for a positive difference. So if we had done the subtraction in the opposite order, if we'd done B minus A and then negative showed us a reduction, then we would test for less than 0, for negative numbers. So let's go with this as long as we know how that's going to affect our test. Even though this data came to us in pairs, we're only interested in the difference. So let's select that column. Let's do a one variable analysis. Let's get our statistics. Notice that our mean is the mean of the differences D, and our standard deviation is the standard deviation of the differences. This tells us our sample statistics, which we can then enter into the workbook. So here's our sample mean of the differences and the standard deviation of the differences. Let's go back to our statistics and select the t-test of a mean. Now remember that our alternative hypothesis is that the mean of the population differences is positive, that is, the cholesterol rates went down. That tells us P and our t-value. So let's enter those, our t-value and our p-value. So that tells us that, well, that's well less than alpha. So we reject the null hypothesis. Now we're going to say this in words, and we say this by saying there is sufficient evidence to say that the cholesterol level of heart attack patients decreases from 2 days after a heart attack to 4 days after a heart attack. Now that's fine, and that's what we did in Chapter 7, is we tested a hypothesis. But it would be kind of nice to know approximately by how much did it decrease. We were simply testing this hypothesis against sigma, a level of significance. But we might want to do a confidence interval. So now we're going back to the concepts of Chapter 8. We're looking at intervals. This is a t-interval. That is because we do not know the population standard deviation. Steps 1 and 3 are the same, so those become steps 1 and 2 in the establishing that we're doing the confidence interval, and our new step 3 is to find the sample statistic and the confidence interval. And then if you're looking at what comes next for the sample statistics, those are exactly what we saw earlier. So that literally is copied and pasted from the difference, the sample mean of the differences, and the standard deviation of the differences from when we were doing hypothesis testing. And again, pairs there, not individual data points, but pairs. So the confidence interval is an estimate of the difference. So if you're asking yourself what that is talking about, that is talking about the difference of the population means. So we're basically now looking at a number by how much it went up or by how much it went down. So we can say that it went down if we've got a positive number. If mu sub 1 is greater than mu sub 2. We can say that it went up if we've got a negative number. If mu sub 2 is bigger than mu sub 1. Okay, so let's look at an example of finding a confidence interval. So it says, use the data to estimate the true mean difference between cholesterol levels 2 days and 4 days after a heart attack at a 95% level of confidence. We're using the same data as before, so if we go back to GeoGebra and go to statistics, we can remind ourselves of the mean of the differences and the standard deviation of the differences. When we go back, these are exactly the same numbers as before. We can enter those. Now let's go back to GeoGebra and get an estimate of the mean using the t-estimate of a mean. We're interested in the 95% level of confidence, so let's make sure that's correct. And now we have our interval. Here's our interval as the point estimate plus or minus the margin of error. Here's our lower limit and our upper limit. So we'll enter that, stating the confidence interval. Now those numbers are positive. which means that the amount of cholesterol did indeed go down. So the statistical interpretation is that there is a 95% chance that the true difference in population means lies between 9.1269 and 36.7398. Now, because we have units, we can say this in a very clear. Between 2 and 4 days after a heart attack, cholesterol levels fall between 9.1269 milligrams per deciliter and 36.7398 milligrams per deciliter. And this concludes our look at 9.2, looking at paired samples of two means, both hypothesis tests and confidence intervals.